Hello everyone, we are group 13 and we will be presenting our project about bundle adjustment. Our group members are Dávid Komorowicz, Desousa and Smirnov Kirill. The project was inspired by the Building Rome in a Day paper. We wanted to reconstruct a scene from lots of images taken from different viewpoints. We used the BAL dataset, which provides point correspondences between multiple cameras, and the Kinect dataset, which provides RGBD images. Furthermore, we used the Eigen, Ceres, and OpenCV libraries. This diagram shows the individual components of our method. First, we implemented bundle adjustment and verified its correctness on the BAL dataset. Then, we started working on the Kinect dataset. We extracted feature points from the color images, matched them to get global correspondences, and lastly, we added the depth from the sensor data. In the following, we will talk about the individual components in more detail. Bundle adjustment minimizes the reprojection error. This is highly nonlinear, non-convex, therefore proper initialization is crucial to the success of the optimization. We therefore initialize the point and camera parameters with the ground truth and perturb them with Gaussian noise to test robustness. The animation shows the optimization process. The green points represent the camera locations.
As for feature matching part, we decided to work with scale-invariant feature transform descriptors, because it's a well-known algorithm that performs sufficiently well in comparison to other handcrafted feature descriptors. And there are 3 implementations available. Once we get key points with their descriptors, we perform matching. We implemented an offline-based approach. In other words, we match features from current frame with all previous frames. If for some key points we haven't found a correspondence, we will not include it in optimization. Our matching algorithm consists of 2 main steps. At the beginning, we use flan-based matcher from OpenCV to get initial correspondences. Then we apply several tests to eliminate wrong matches. Firstly, we run lowest test, which basically ensures that the distance between 2 best matches is big enough. Secondly, we run a run-suck algorithm, which provides us a fundamental matrix. We use this matrix to remove correspondences that violate geometric constraints. More specifically, we expect that all key points move in the same direction. Despite the fact it might sound a little bit unintuitive, we saw an improvement in optimization in terms of error. Moreover, all our tests remove only 5% of all matches, which doesn't sound too bad. Finally, you can see a distribution of matches over all frames, which we believe looks like a real piece of art.
Once we filter for high-quality correspondences, we can initialize our camera extrinsics as well as the position of our points in 3D space with respect to the world frame. To initialize, we use the procrust algorithm. The red points in the image represent the ground truth of the camera positions in the Freiburg dataset. The green points represent our estimation of those positions using procrust. The blue points represent our position parameters for the camera prior to running the procrust algorithm. As you can see, procrust was able to effectively approximate the ground truth positions. To initialize the points in 3D space with respect to the world frame, we simply change the frame of reference of a point from camera space to world frame using the inverse of the extrinsics matrix. To rid of noise from the depth sensor, we applied bilateral filtering. As you can see, filtering was only activated around depth bins, where there were sudden changes of depth between neighboring pixels. Also worth noting is the amount of visualization we had to implement. In order to develop effectively and to debug quickly, we needed to implement many different approaches to visualizing the data.